Today, the next questions we will discuss of chapter number 11, Human Eye and the Colorful World. So, we were on question number 5 of exercise. Question is, a person needs a lens of power minus 5.5 diopter for correcting his vision, his distant vision, and for correcting his near vision, he needs a lens of power plus 1.5 diopter. So, what is the focal length of the lens required for correcting the distant vision and near vision? So, we know that for distant vision, focal length is negative because it is concave lens is used, and power is also negative. So, the power of the lens of focal length f is given by the relation. What is the relation between power and focal length? This you have learnt in chapter 10. P is equal to 1 upon f. So, in first case P is given minus 5.5 diopter. So, we will put the value and find out f, and that the value of f comes to be minus 0.181 meter. And then in second case, to correct the near vision, the power is given plus 1.5 diopter, and the focal length, again we will apply the same formula. P is equal to 1 upon f. So, f is equal to 1 upon p. Put the value and we get the value of f, and that is 0.667 meter. And focal length of the lens for correcting the near vision is this. So, in first case, which type of lens is used? Concave lens, whose power and focal length both are negative, and in second case, convex lens, power and focal length are positive. Then question number 6 is, the far point of the myopic person is 80 centimeter in front of the eye. So, what is the nature and power of the lens required to correct this problem? The individual is suffering from myopia. So, in this defect, the image is formed in front of the retina. This I have told you in my video lecture when I taught you the defects, eye defects, myopia. We saw that the image is always formed in front of the retina when the person is suffering from myopia. So, the concave lens must be used to correct the defect. Then image distance, that is u, is equal to infinity. So, always in myopia, we take the object distance means u as infinity, because the far point for normal eye is infinity. Then image distance, that is v, is minus 80, that is given in the question, and we take it in minus. So, we have to find the value of f, and we apply lens formula. We know lens formula, we have learnt in chapter 10, 1 upon v minus 1 upon u is equal to 1 upon f. We put all the values and find out the value of f, and that comes to be minus 0.8 centimeter. Now, we know that power is equal to 1 upon f, and f must be in meters. So, power will be minus 1.25 diopter. So, a concave lens of power minus 1.25 diopter is required by the individual to correct this defect. Now, question number 7, make a diagram to show how hypermetropia is corrected. I have shown this diagram. This we have done in the correction of the hypermetropia also. And the near point is given 1 meter, means 100 centimeter, and what we have to find the power of the lens and assume that the near point of the normal eye is 25 centimeter. So, the individual is suffering from hypermetropia, can see the distinct objects clearly, but he or she will face difficulty in clearly seeing the objects nearby. This we know. So, this happens because the eye lens focuses the incoming divergent rays beyond the retina. It means the image is formed beyond the retina, behind the retina. So, this is corrected by using the convex lens. So, we use the convex lens of suitable power and to correct this defect, and again image is formed on retina as shown in the figure. We have used convex lens and the image is formed on retina. Now, we have to find the power also. So, in this case, we take u as minus 25 centimeter, that is the near point of the normal eye, and v is minus 1 meter, that is given in the question, and this is minus 100 centimeter, sorry, it will be minus 100 centimeter. And then we apply again lens formula, 1 upon v minus 1 upon u is equal to 1 upon f. Put all the values and we get the value of f, that is 0.33 centimeter. Now, we will apply the formula of power, p is equal to 1 upon f, and we find the value of power, and that comes to be plus 3 diopter. The next question is, why is a normal eye not able to see clearly the objects placed closer to the 25 centimeter? So, the normal eye is not able to see the objects placed closer than 25 centimeter clearly because the ciliary muscles of the eyes are unable to contract beyond the certain limit. So, there is a limit up to which the ciliary muscles can contract the eye lens. So, that limit is 25 centimeter. So, beyond that limit, the eyes cannot see clearly. Now, next question is, what happens to the image distance in the eye when we increase the distance of the object from the eye? then image is always formed on retina, even on increasing the distance of the object from the eye. Whatever the distance of object is, the image must be formed on retina, then only we will able to see the objects. For this, eye lens becomes thinner and eye with the help of ciliary muscles, and its focal length will increase and the object is moved away from the eye. So the image will be formed on retina, so image distance will remain same. Now next question is, why do stars twinkle? So stars twinkle, first point is due to atmospheric refraction of starlight, and the starlight on entering the Earth's atmosphere undergoes refraction continuously, because there are the physical conditions are not stationary and before it reaches the Earth. The atmospheric refraction occurs in a medium of gradually changing refractive index. Refractive index is gradually changing when we move towards the Earth. That is why, due to this atmospheric refraction, stars appear to twinkle. The starlight fluctuates and that flickers and when fall on our eyes. So the star sometimes appears to be bright and sometimes dim. That is called twinkling of stars. Then next question is, explain why the planets do not twinkle. Unlike stars, planets do not twinkle. Why? Because stars are so distant and they appear to be point-sized sources of light. But the planets are much closer to the Earth, and they can be considered as the extended source of light, and we can consider a planet as a collection of many point-sized sources of light. So the total variation of the amount of light that falls on our eyes becomes zero, and it nullifies the twinkling effect. So the planets do not appear to be twinkle. Next question is, why does the sun appear reddish early in the morning? While light coming at that time, at the time of sunrise and sunset early in the morning, the sun is at near the horizon, and from that horizon point the starlight has to cover many thicker layers and a longer distance. So the light of the shorter wavelength gets scattered away in the path. So the light which reaches on our eyes, that is of longer wavelength, and longer wavelength is of red color, so it appears to be red. And last question is, why does the sky appear dark instead of blue to the astronauts? Because in space there are no particles to scatter the light, so sky appears to be dark. So these questions you will do in your fair notebook. Thank you.